There we go. So we're recording now, and here we go. So we're going to start on infinite sequences and series. So an infinite series gives us a precise way to express many numbers and functions, both familiar and new, as arithmetic sums with infinitely many terms. So for example, we can see that pi over 4 will actually equal 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and you can continue on in that same fashion, going on the integers, the odd integers in the denominators and alternating your signs with plus minus like that, and you will find that it is pi over 4. So I'd like you to real quick go ahead, grab a calculator, type in pi divided by 4, hit enter, and then try typing in those first few terms of our series and see how close together they are. Of course, the further you keep going, the closer and closer together these will get. Go ahead and give it a try, just to see. If you just do like the first 2 or 3, you'll get kind of close. If you do all 5 of those, you get closer. If you keep adding more and more of them on, you'll get closer and closer.
I got 0.839.
For what?
For the other side.
You got what?
For the like 1 plus
1
minus 1 over 3, I got 0.8349.
Okay.
Is that what it is?
Well, what's pi divided by 4?
0.78.
Okay, keep going. They should get closer, especially as you add more terms. Keep doing more terms, they'll get closer and closer together. All right, starting to go together. All right, so that's what that one is, what that one will equal to. We don't always have to just have a constant that it equals to. We can actually express certain functions, which I believe I made mention of before. We can express them as an infinite series. So cosine of x is actually 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720, and so on and so forth. And so you can, as long as you're using numbers that are, I believe, near 0 in radians, you can actually plug those in and come up with cosine purely with just addition. This is the way at least calculators used to do it. They would do the series of it because calculators really can only add. In fact, that's what computers do. They just add numbers together. So you find a way to figure out what cosine is just through adding, and that's what they do there. Just do a bunch of terms of that and add it all up together. So basically our goal here is to approximate. All right. Something like sine of theta is approximately equal to theta for small theta. Or if we're looking at something that's turned on a curve like this, we can actually go in, we turn to some angle over here. This actually has to do with that there. We have this little extra little bit here. This would be the angle theta, and we can say that cosine theta here times r is actually just theta squared over 2 times r. So just little approximation things. Don't worry about how I necessarily came up with those at the moment, just some examples. So let's take a look down here. The difference between a sequence and a series. A sequence is a list. All right, this is a sequence. It's a list of numbers or a list of items, right? Kind of almost like a set of something, right? And we can have A1 and then A2 and then A3, and it can go on forever. That's basically a list. A series, on the other hand, is where we're summing the members up. It's like a sequence, but we're adding all of the members together. So it's the sum of all the members, okay, like that. So it'd be A1 plus A2 plus A3 plus so on and so forth. And so you end up with a number or plus or minus infinity when you do that, instead of just a list of things. All right, any questions on this first page? Difference between sequence and series? No? All right. Representing sequences. A sequence is a list of numbers, like I just did a second ago. A1, A2, A3, dot, 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 A sub n, so on and so forth, like that. The integer n that is on there, the integer n, is called the index of A sub n and indicates where A sub n occurs in the list. Is it the first one, the 100th one, the millionth one? Where is it? It just tells you how many terms in you are at. Examples here, sequences can be described by writing rules that specify their terms. So each A sub n there is the square root of each n, right? So you'd have square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, so on, so forth like that. Or here, nice little trick here, B sub n. If you notice on this one, what's going to happen to the sign of each member of this list? It's going to alternate. You have that -1 and then raised to a power, right? So when that power is even, it's going to be positive. When that power is odd, you're going to have a negative term. So you can alternate signs, which we saw on the examples there on the previous page, right? Alternating signs. Here, n minus 1 over n, and then of course -1 to the n plus 1. That one's just going to alternate. Just going to alternate signs. +1, -1, +1, -1. Or instead of coming up with some sort of algorithm that comes up with them, you can also just list their terms. So and if there is a pattern, then you list the terms and you can make the pattern evident. So, and then this would be 1/3, and just alternate our signs back and forth, right? Which is just oh, I put a comma here. I meant to put a times. Sorry. 1/3. And C sub n. I'll do one more here. N minus 1 over n. So that's 1 minus 1. That's a 0 on the top. So 0. And then 2 minus 1 over 2, right? 1/2, 2/3, 3/4, so on and so forth. Okay. So these are our sequences. And we can also just sometimes write a sequence using its initial rule. So we can write a sequence A sub n equal to square root of n from n equals 1 to infinity. Okay. Done with that page. Any questions so far? All right, let's go on. So here we have a graphical representation of sequences. Here for the square root of n, you can see we just start off with 1, and then we just keep going, A1, A2, A3, A4, A5, and they're on a number line. We can also represent them with 2 dimensions there on axes where we're relating n to a sub n, and you can see we get a nice little graph going there. It's almost like we're getting that straight line, but we're taking steps instead of going continuously. We're only going through the integers. Here's 1 over n. You can even see that kind of shape you'd get going down there if it was continuous, right? And then you can see them on the left there with the number line moving to the left, starting with A1 and then getting smaller and smaller and smaller and approaching to 0. And then that other one, the last one we did, jumping back and forth, up above and down below, above and below the n axis, I guess they're the horizontal axis, going back and forth like that. Okay. So let's try some of this. Find the values of different versions, A1, A2, A3, and A10 for the given formula. So this is 1 over n factorial. Do we all remember how to do factorials? We done factorials so far in this class? So like, yeah, you just keep stepping down and multiplying them all together. So A sub 1 is going to be 1 over 1 factorial. What's 0 factorial, by the way?
I want to say 0, but I think
Ooh, we might have to look into that. It's 1, by the way. 0 factorial is 1. We'll have to look into that. You can do it by looking at like 5 factorial, and it's 5 times 4 times 3 times 2 times 1, and then 4 factorial is 4 times 3 times, and just work your way back up, and it implies that 0 factorial is 1 if you keep following the pattern. So this is 1 factorial, and this is 1 over 1, which is 1. A sub 2 is 1 over 2 factorial. And that's going to be 1 over 2 times 1, which is 1 over 2. A sub 3, 1 over 3 factorial there. 1 over 3 times 2 times 1, which is 1 over 6. And then A sub 10, go down here to do the 10th one, is 1 over 10 factorial. 1 over 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Anybody want to tell me what they think that is? Oh, no calculators. Go ahead, what is it? Okay, that's all right, I have it here. Oh, I think I wrote 800 there. Okay. Oh, and 10 factorial gets big real fast, doesn't it? Okay. What about factorial? What about that next one? Why don't y'all try writing 1, 2, and 3 out, and 10. Hmm?
I saw the, how they're all related.
You did all 4 of them?
I did the first 3. You want to see?
And do the 10 one. You're gonna guess?
They all show the same pattern.
Hmm. So B1 was what? And B2 was what? And B3 was? And B10 was? Good. If you look at this, this is what? 2, that's not a good 2. 2 to the n minus n plus 1, right? And what's n minus n plus 1? Nope. This is 2 to the n minus 1. 2 to the minus 1, which is 1/2. So they're all going to be 1/2. Okay. Any questions so far? All right. So let's take a look then at convergence and divergence for our sequences. Let's talk about our formal definition here first. Formal definition of convergence in sequences: the sequence A sub n converges to the number L if for every positive number epsilon there corresponds an integer n such that A sub n minus L is less than epsilon whenever little n is bigger than greater than. If no such number L exists, we say that A sub n diverges. Essentially what we're saying is, do the numbers approach a value? As we keep going out, do they all get closer to 0, or do they all start getting closer to 2 or something like that? Or do they blow up to infinity or blow up to negative infinity or something like that? Okay, then they diverge. All right, so they may come up and kind of plateau at something like a horizontal asymptote almost, kind of a thing. Which one? Well, we'll talk about that in a few minutes here. We'll look at. We're about to right now talk about this. So if A sub n converges to L, we write the limit as n goes to infinity. A sub n is going to equal L. Or you can write A sub n goes to L. And then we call L the limit of the sequence. Okay, and so you can see that in that picture. We're approaching that L, and there is some epsilon there that is always going to be, when we go plus or minus epsilon, all the values are going to wind up in between them. There is some actual epsilon that works out there. So very similar to like what we did with, or what y'all would have done taking limits. I guess that wasn't with me. So example 1, here we can easily show that the limit of 1 over n as n goes to infinity is 0. And the limit as n goes to infinity of k is k, because it's just a constant, right? Constant. Okay, so constant k, so the limit as n goes to infinity of 7 is 7. So, and then we have our theorem here where we're going to say we have set, or we have sequence A sub n and sequence B sub n. They're both sequences of real numbers, and let A and B be real numbers. The following rules hold if the limit for A sub n is A and B sub n is B. So we have the sum rule. If we're adding up those, then it's just A plus B. The difference rule, you can see that there, it's the difference of the two. Multiplying each term by a constant multiple, we can bring that out front. Product rule, just the product of their limits, and then the quotient rule is just the quotient of their limits, assuming the denominator one is not 0. Okay, so now let's take advantage of these and see if we can look at some sequences. Right? Now, show that the sequence 3 plus 0.4 to the n goes from 1 to infinity, converges. All right, any ideas on how we can do this one? Start off by doing what? Yeah, take a limit. Limit as n goes to infinity of 3 plus 0.4 to the n. There we go. Now what can I do? Make it 2 limits. Good. Limit as n goes to infinity of 3 plus the limit as n goes to infinity of 0.4 to the n. And that's, we've just used, just using our rules from before, right? From the previous thing. So we also had we have the limit there of 3. What's that one going to end up being? 3. And then this one is, we can look at it this way if you want. You can make it the limit of n, as n goes to infinity, of 4/10 to the n. And what's going to happen as we keep multiplying that together? 4/10, 4/10, 4/10, 4/10. It's going to go to 0. It's going to get smaller and smaller. And so we'll end up with 3 plus 0, which will just be, anybody? Good, 3. Okay. So it converged to 3, so we showed it converged. It converges. All right. Take a look at this next one. I'm going to give you a little few minutes here to try that one. Okay. I'll pause here. All right. So for this one, what's the first thing I need to do? Limit as n goes to infinity, 1 minus 2n over 1 plus 2n, like that. And then what did I do? Then what do you do here? What do you mean you use a quotient rule? Well, if we plug in infinity now, don't we get infinity over infinity? Oh. Or how about this one? How about that? Remember these ones now, right? Let me do something like that. Okay, and then, of course, if we then take the limit, we end up with 0 minus 2 on the top and 0 plus 2 on the bottom. which is -2/2, which is -1. Okay. All right. Okay, so all right, so real quick here on the last page, next page here is divergence to infinity. The sequence A sub n diverges to infinity if for every number m, there is an integer n such that for all little n larger than the capital N there, A sub n is greater than our m value. So in other words, essentially, we can always find the next value being larger and larger and larger and larger, okay? So every value we get, there's always at least one more that's bigger than it. And then if we go to that one, there's always at least one more that's bigger than it. That means it's going to diverge. So in other words, what we say here is the limit as n goes to infinity of A sub n is going to be infinity. We can also just say that A sub n goes to infinity or diverges to infinity. You can do similar sort of thing except for to negative infinity. For every one, there's always one smaller or more negative, I should say, as you go down. Okay, and that's it for the idea of what divergence is there. And there's an example of a sequence that diverges. Okay, all right, we'll stop there for today and continue.